Hey everyone, I hope you're doing well today. While my last video was part 1 on linear equations, this will be part 2. Just to give you a quick recap, in example 1 we talked about the difference between independent and dependent variables. And in example 2, we were practicing using a linear equation and filling in a table when we were given some x values. And in example 3, we practiced coming up with a linear equation when we were given a table. Now that you hopefully understand the basics a little bit better, let's continue learning about linear equations with example 4. In this example, we're going to take our understanding of linear equations and the tables that represent them and transfer it onto a graph. Let's start by looking at this table and seeing if we can come up with a linear equation that represents it. From the previous video, try to remember that we write our linear equations in this form. Our dependent variable will be isolated on one side of the equation. Then we'll multiply our independent variable, or x, by some coefficient. If we need to go bigger, we'll use a number bigger than 1, and if we need to get smaller, we'll use a proper fraction. And to the right of that, we're either going to add or subtract a number. If we need to go bigger, we'll add, but if we need to go smaller, we'll subtract. For this particular table, we can see that each of these x values help create larger y values. Since that's the case, I'm going to start by thinking about multiplying. Just looking at this 2 and 5 here, we can multiply 2 by 2 to get 4 and add 1 to get 5. Let's see if that works here. 4 by 2 gets us 8, and 8 plus 1 gets us 9. And checking just one more for now, 6 by 2 equals 12, and 12 plus 1 does equal 13. After checking a few of these, I think it's safe to say that we're going to multiply each of the x values by 2, and then we're going to add 1 afterwards. Therefore, our linear equation here is going to be y is equal to 2x plus 1. Now let's graph it. First, take a look at your x values and see what the highest number is. Since we have 8 and we have more than 8 boxes, we're going to be able to write all of them down. As for the y values, they go all the way up to 17, and we don't have 17 boxes. In order to make it fit, we can make each box worth 2 along the y-axis. Now it's time to plot some points. Our first x and y pair is 0 and 1, so that's going to be the ordered pair, 0, 1. And we're going to plot that right here on the y-axis. This 2 and 5 make the ordered pair 2, 5. And from the origin, that's 2 to the right and 5 up, which is right here. Then we have 4, 9. From the origin, that's 4 to the right and 9 up, which is right here. Then we have 6, 13, which is right here. And finally, 8, 17, which is right about here. If you plotted your ordered pairs correctly, you should be able to connect them with a straight line. Remember, the word linear in linear equation represents a straight line. This is the linear graph that represents the data table we were given from the start. Let's take a look at this table now. It's important that you notice that each of these x values somehow generally gets us a lower y value. While 0 gets bigger to 2 and 3 stays the same as 3, as you become 6, 9, and 12, you can see that each of the y values are always smaller. Because of that, it makes me think that we're going to have to divide these x values or multiply them by some sort of fraction to make them smaller. Since all of these x values are divisible by 3, I'm going to try using 1/3 as my coefficient for x. If we were to multiply each of these x values by 1/3, it's the same thing as dividing each of them by 3. Multiplying this 1/3 by 3, we're just going to get 1, and we would have to add 2 to get the 3 beneath it. Let's see if that rule works for this 6 here. Multiplying 6 by 1/3, that equals 2, and then we'd have to add 2 more to get to the 4 underneath it. And just testing one more here, if you take 1/3 of 12, that's going to be 4, and you have to add 2 to get the 6 beneath it. At this point, hopefully you're convinced that we're going to take 1/3 of each of the x values and then add 2 on afterwards. So our linear equation here is going to be y is equal to 1/3 times x plus 2. Now it's time to graph. Since our x values here go above 10 and we can't fit it on the graph, let's be creative with how we spread them out to make them all fit along the x-axis. We can make each box worth 1.5, and we could put 3 over here, 6 over here, 9 over here, and 12 over here. As long as we space them out all evenly, we're good to go. As for the y values, it seems like the highest number we need to go to is going to be 6. Since we have 10 boxes, we can just go by 1 here and use 6 of them. These pair of numbers of 0 and 2 make the ordered pair 0, 2. I can plot that right over here. These make 3, 3. Going to go right around here. This is going to be 6, 4, which is right over here. Then we have 9, 5, which is right here. And finally we have 12, 6. That's going to go right here. Once you're done plotting your ordered pairs, we should get a straight line again. The key takeaways for this example are to make sure that you space out your numbers appropriately along the x and y axis, use the numbers in the tables to create ordered pairs, and make sure you get a straight line when you're done. In this example, let's practice graphing when we're given the linear equation. Here we have the linear equation y is equal to 4x minus 2. And when you're given a blank table, feel free to choose any x values you'd like to plug into our equation. When x is 0, we have 4 times 0, which is 0, minus 2, which is just equal to negative 2. When x is 1, we have 4 times 1, which is 4, minus 2, which is equal to 2. When x is 2, we have 4 times 2, which is 8, and 8 minus 2 is equal to 6. When x is 3, we have 4 times 3, which is 12, minus 2 is equal to 10. And when x is 4, we have 4 times 4, which is 16, minus 2, which is equal to 14. Now that we have a table of values, let's get them onto a graph. Our highest x value here is 4, and since we have 10 boxes, I'm going to spread them out and put a 1 over here, 2, 3, and 4. Our highest y value is 14, and since we only have 10 boxes, we're going to have to go by at least 2. Plotting this 1, 2 is going to be right over here, 2, 6 is right over here, 3, 10 is right here, and 4, 14 is right over here. Now go ahead and connect these dots and put an arrow on each end. There's the graph for this linear equation. Now let's look at this equation where we have y is equal to 2/3 times x plus 4. While we can choose any x value we want for the table, you want to be strategic when we have a fraction coefficient. Because we have a denominator of 3 for our coefficient, we're going to want to choose multiples of 3 for x so it cross-cancels nicely each time. For the x values here, I'm going to choose 0, 3, 6, 9, and 12. Substituting in 0 for x, we have 2/3 times 0, which is 0, plus 4 is equal to 4. When x is equal to 3, 2/3 of 3 is just equal to 2, and 2 plus 4 equals 6. When x equals 6, 2/3 times 6, or 2/3 of 6, is equal to 4, and 4 plus 4 is equal to 8. When x is equal to 9, we have 2/3 of 9, which is 6, and 6 plus 4 is equal to 10. And when x is equal to 12, 2/3 of 12 is equal to 8, and 8 plus 4 is equal to 12. Because our highest x value is equal to 12 on our table, I'm going to space these out and write 3 over here, then 6, then 9, then 12. Each box here is technically worth 1.5. And for y values, we have even numbers, so I can go by 2 and definitely get to 12. Now let's plot some points. 0, 4 is right over here, 3, 6, right over here, 6, 8 is right over here, 9, 10, and 12, 12. Go ahead and connect those to make a straight line, put some arrows on it, and there's your graph for the equation. Let's talk about some key takeaways here. First, when you're making your table, feel free to choose any x value that is convenient for you. If you have a fraction, be more mindful so you can cross-cancel the denominator. Once you choose your x values, you just need to substitute them into the equation because the y values depend on it. Once your table is complete, you can plot your ordered pairs, connect the dots, and draw some arrows. In this example, we're going to try to put everything together that we learned from the first 5 examples all into one. Our situation here is that Finn has already scored 8 goals in soccer this season, and he continues to score 3 goals per game. The independent variable in this situation is going to be the number of games. And the dependent variable of this situation is going to be the number of goals. The number of goals that Finn can score will depend on how many games he actually gets to play. For our independent variable, we can use x to represent it, and for our dependent variable, we can use y. Let's make a table now. For our x values, we'll have 0 soccer games, 1 soccer game, 2, 3, and 4 soccer games. If we think about it, if Finn doesn't play any more soccer games, he's still going to have the 8 goals that he already scored. Now if x is 1 and he plays 1 more soccer game, he's going to have a total of 11 because he scores 3 more goals. Now if he plays 2 soccer games and scores 2 goals each, 3 times 2 is equal to 6, and 6 plus the 8 he originally scored is equal to 14. Continuing this pattern, in 3 games he'll have 17, and in 4 games he'll have 20 goals. And for our linear equation, we're going to have y equals, and he's scoring 3 goals per game, which is going to be 3 times x, or 3 times the number of games, and we'll add on our constant here of 8. Remember that this y here represents the total number of goals that Finn has scored, and that's going to be dependent on these 2 things on the right. This 8 represents our constant term because these 8 goals that Finn already scored can't be taken away and can't change. And this 3x over here represents our variable term, or our rate. X represents the number of games, and as more games are played, Finn's going to score more goals. So again, the y, or the total number of goals, will depend on everything on the right side. There's our linear equation. For our x-axis, we only need to go to 4, so we can make this box 1, then 2, then 3, then 4. And for our y values, we need to get to 20, so I'm going to skip count by 2's. Then be sure to label your x-axis as the number of games. In general, it's important to have a title for your graph so you can have fun and make something up for that. And finally, let's start plotting some points. And once you're done plotting your points, connect them with a straight line and put some arrows on it, and there's your graph. In general, when you're given a word problem, start by identifying your independent and dependent variables, then come up with a table for values that make sense for the situation, followed by a linear equation that can represent any possibilities, and finally put it all together on a graph. And while the graph only goes up to 4 soccer games, the power of this equation is that we can plug in any value of x or any number of soccer games to predict how many goals Finn will have in total at this given rate. Maddie has already played 3.5 hours of a game called Roblox. She then continues to play 1.5 hours per day. And just like the last example, let's start by identifying our independent and dependent variables. In this scenario, the independent variable is going to be the number of days that go by. And we can use x to represent this. And the dependent variable is going to be the number of hours that she plays her video game. We're going to call that one y. While both variables are a form of time, the amount of time that Maddie spends playing Roblox is going to depend on how many days actually go by. Hopefully it makes sense that as more days go by, Maddie's going to play more Roblox. Now for a table here, I'm going to choose the numbers 0, 2, 4, 6, and 8. The reason why I chose even numbers for the x values is that when we multiply by the 1.5 later on, we won't have to deal with as many decimals. If 0 days go by, Maddie won't be able to play any more Roblox, and the total here will be 3.5 hours. Now when x is 2 and 2 days go by, and she plays 1.5 hours per day, 1.5 times 2 is going to be 3, and 3 plus the 3.5 hours is going to be 6.5 hours. When x is 4, or 4 days go by, 4 times 1.5 is equal to 6, and 6 plus 3.5 is going to be a total of 9.5. If 6 days go by, 6 times 1.5 is equal to 9, and 9 plus 3.5 is equal to 12.5. And when x is 8, or 8 days go by, 8 times 1.5 is going to be 12, and 12 plus 3.5 is going to equal 15.5. Our linear equation here is going to be y is equal to 1.5 times x plus 3.5. This constant term of 3.5 represents the 3.5 hours that Maddie has already played, and this 1.5x represents the fact that Maddie's going to be playing 1.5 hours per day. Now let's make a graph. We can put the number of days over here along the x-axis, and the total number of hours Maddie spends playing Roblox along the y-axis. And once you give the graph a title, let's plot some points. Once you finish plotting your points, draw a line and put some arrows on it. When you look at this graph, you can visually see that when 6 days go by, Maddie plays 12.5 hours of Roblox. And the cool thing about the equation is that you can predict how many hours she'll play Roblox for any given number of days. And that wraps up the last example for this video. I hope you found this video helpful in tying all the concepts together from independent and dependent variables, tables, linear equations, and graphs. As always, keep up the good work, and I'll see you in the next one.